All right, so here is an example for class 15. This is the sample problem 6.1 out of the textbook. There's a lot here. I don't know if I'm going to be able to fit it onto one page, and I don't know why I'm recording myself with this wonderful hair. Okay, so what we're going to do is use the method of joints and determine the forces in each member of the truss shown. So what we want to do first is figure out what the reactions at E and C are going to be. So we need to do the FBD of the entire truss. All right, so like I know that I need to conserve paper here, so I'm going to try to make this efficient, but not too small. One thing, the book runs through this example, but I like to approach things my own way, so a little bit differently. What I think is maybe more systematic. Instead of using the fact that I believe this is a 3, 4, 5 triangle of some sort, right? Because this is 6 right here, and this is 8, so you could assume that this is going to be 10 right along the length of this. I went ahead and figured out the angle there, so if I call that theta, right here, I see that theta was the inverse tangent of rise over run, which is the opposite, or opposite over adjacent, so that's going to be 8 over 6. And I get a familiar 53.13 degrees, which is, something I usually tell you that it's 3, 4, 5 triangle. I think the complement is 36.87 degrees. So when you see those, you know that you have a 3, 4, 5 triangle. But that was just something I was going to do to get out of the way. So we get 1,000 pounds right here. This is a sliding joint, so that's only upwards. I'm going to call this RE. And then I'm going to choose these two reactions right here. I'm going to call them RCX and RCY. I'm going to choose them by default, making them positive. We could put some dimensions on here if we want to. This is going to be 8 right into there. This distance from here to here, let's see, this is going to be 12. Put that in there. And this is 12. I don't know if I don't think I need anything else. Maybe I also need to know that this is 6 right in there. So if we take the sum of the moments, let's take it about C equal to 0. And so we take 2,000, it's positive, times 24, because it's going to be counterclockwise, plus 1,000 times 12. And then we're going to have a negative RE, and it's going to be times 6. And we find out that RE is 10,000 pounds. And it is upwards, because we will get positive answer out of that. By observation, we could see that there's no forces in the x direction except for that reaction. Therefore, just writing the thing out for the sake of completeness, we'll say that RCX is equal to 0. Some of the forces in the y direction equal to 0. And we have a negative 2,000 downwards, negative 1,000 downwards, and then we're going to have 10,000 upwards plus 10,000, and the comma kind of got in a weird spot. You don't have to fix that kind of thing, but it's okay. And then we have RCY coming upwards, and we could already see that we're going to get a negative RCY. I don't know why I started writing it C. RCY is a negative 7,000. Could have done that in our heads. So just to keep in mind, that's drawn wrong now, right? So if we keep going someplace else, we don't want to be distracted by that. Now we want to use the method of joints to go through there and march through. So we could start in a bunch of different places. One of the confusing parts of this approach is that there are decisions that you could make. But if you make a decision and you get to a spot where you're like, oh, I can't quite figure that, just put that to the side and go to a new spot and try that out. But let's start out with A. It's as good as any. So we go at A, and we'll make a free body diagram. And now we're really just doing particles. They're actually, in the method of joints, these are all just particle FBDs. I'll declare X, Y, and I guess I'll put it underneath it. I just didn't want to use up too much space. So we have 2,000 down at A. And now we want to draw these lines right here. And we can use a logic to apply what direction these are going to go in. First off, this thing is completely up and down. This has no vertical component to it. These are all two force members. All the joints are pinned. So this guy has to be coming upwards to counteract the vertical part of that 2,000 pounds. That's the thought process you want to try to develop here. And I'm going to label this as FAD. I just go alphabetical order. I don't bother deciding, oh, this one's going in that one direction, that direction. Just generically, I'll just go alphabetical order when it comes to subscripts. And so then we're going to have FAB. And now that we know this direction, that's this one is the only one that has a horizontal component, and this one does too, right? They both have horizontal components. So if this one's going to the left, this one has to go to the right. That's the only way that these are going to balance. So that's the mindset that we want to have. And that angle right there, as we found, was 53.1 degrees. 13 degrees. By the way, it would be easier to use the 3, 4, 5 triangle, but I never feel comfortable with it. I just prefer using the angles to the thing. It's just an idiosyncrasy, maybe. Idiot-syncrasy, no. So let's see. I will use the, we have to use the vertical direction first. So sum of the forces in the y direction equal to 0 here. Declare it as positive. We have a negative 2,000. And then in the positive direction, we have a FAD. And so that's going to be, we ended up being the sine. Did I do that right? Yes, I believe so. 53.13, the sine of that equals 0. And we get an F. AD is going to be equal to 2,500 pounds. And here's it becomes the first thing. Is this compression or tension? That one right there. Well, remember how equal and opposite all the time. Equal and opposite, equal and opposite. And remember that these are free body diagrams and the forces are on them. So this is the force on the pin, not in the member. So the pin is being pushed by this. So this is pushing back onto the member. Say it again. Important distinction. This is the pin, and these are forces of the members onto the pin. So if this is pushing the pin, then the pin is pushing it. Therefore, this is a compression. You want to own that. You want to really, you want that to be like to really believe it. So just make sure that you run that back, convince yourself, and then push yourself to get it right, and correct yourself when you get it wrong. Okay. So now that we have this, we're able to get the x direction. This is the logic that we're applying here, right? So in the x direction, yeah, okay. By the way, I want to check something out here. Do I have two of these open? No, I'm good. Okay. In the x direction, I have a negative 2,500, and now I'm going to go cosine of 53.13, and then I'm going to go a positive FAB equal to 0. So FAB is now going to be 1,500 pounds. And now I got to ask, is it tension or compression? Well, the force of the member is pulling on the pin. Therefore, the pin is pulling on the member. It's got to be in tension. Right? Now, you could try to memorize which way these arrows go here, or you could think it through this way. All right, so now we have this member and this member. We know this. So we could actually go here or here, but because there's a member right there, it makes more sense that we're going to go to D next. If we happen to go to B and get stuck, we could just start writing the thing out, get stuck, and then go down later. But it's probably easier to read the thing to go through the same type of approach on here. Okay, so we want to do an FBD of this pin at D, and we'll draw the lines first. I'm going to take a look right here. We'll notice that this right here is going to be that same 53.13 degrees right there, right? And I drew a line in here, but that was supposed to represent just that it was symmetric onto there. Okay, so what we do know now, all right, so we could actually label these if we want to. This is going to be FAD right here. This will be FBD right here. And then this would be FDE here. And which way does FAD go? Well, it was pushing onto this, right? It was in compression, so it's going to be pushing onto there, right? That's the direction FAD, and we know this one. Now, if that's going downwards, this one has to go upwards. Does that make sense? Because this is only going horizontally, so this has to be in that direction. Now the next logic is that's going to the right and this one's going to the right. So this one has to go to the left. That's the kind of logic, right? And so if we want to find, we need to find the vertical component. All right, so we have we have this guy, and we know, by the way, that's also 53.13 degrees. So we could actually make a determination just based symmetry. This has to have the same magnitude as that. But we could also write it out, right? So the sum of the forces in the y direction have to equal 0. And so we have a negative, and so the value of that is 2,500, negative 2,500. And that's going to be the sine, right? The sine of 53.13. Now we want the vertical part of this, and that is upwards, FBD, and we also take the sine of 53.13. So you could see we've already convinced ourselves, right? That boom, boom, that FBD is equal to the 2,500 pounds, but this one's in tension, right? Because it's pulling on the pin. The member is pulling on the pin, so the member is also being pulled upon. So they're in tension. And I didn't do a good job with my margins there, did I? And then so in the x direction, we say, well, look at this. This is positive right here. So we got a 2,500. Now the cosine of 53.13. And then this too is also 2,500. So 2,500 cosine of 53.13. And now this one is negative FDE. And that's equal to 0. So FDE, we put those things together, and FDE ends up being 3,000 pounds, and it's pushing, so it's getting pushed on, so it's compression. Now we know this member, this member, this member, and this member. Therefore, maybe it makes sense to go to B. We might have been able to go to E. No, I don't think so, because we didn't know this member and this member. But we're going to go to B next. All right, is that true? Okay, yes. So at B, we draw B. It's horizontal and has the two down things. Okay, so we have a bunch of things going on here. And right there. That thing is coming down, and there's your 1,000 pounds. We already know these right here, right? So this was FAB. This is FBD. This is FBE. And this is FBC. Okay? So for the AB is in tension. So it's going this way. BD is also in tension. Right here, right? It was in tension. So it's coming this way. It's pulling out. Looks like my office hours are starting soon. Until I hear the magic bell going. All right, so one thing we notice is that's down and that's down. This one has to be up. And that's the one that we'll do first, right? The next part of it we're not. Well, okay, yeah, it looks like everybody is, this is going left, that's going left, that's going left. This one must be going right, all right? That's the logic. So some of the forces in the y direction is a good place to start here, because we know this, we don't know that, so we'll be able to find that. It's equal to 0, and so we have a negative 1,000 coming down. We have a negative FBD, which we found to be 2,500. And this 2 is our 53.13 right in there. Right in there is 53.13 as well. And so let's see, that's going to be the sine of 53.13. Let me double check that I got that right, as I'm trying to think as I do this. Yes. And then we're going to have a plus, because this one's up, FBE. And that 2 is going to be the sine of 53.13. And I believe that's going to equal 0. Did I do that? I think I got all that right. Double checking. Okay. And then FBE is then equal to 3,750. And that's going to be in compression, right? Because it's pushing on here, so this thing's pushing on it. Some of the forces in the x direction. We know that FAB is a negative. Is that the 1,000? No, that's the FAB is the 1,500. The negative x direction. FBD is also, that's the 2,500. But we want the cosine of our 53.13. And then we have a negative 3750, and that's also cosine of 53.13. And then lastly, we have a positive FBC that equals 0. FBC is therefore going to be 5,250 pounds, and that's pulling on that thing, so it must be tension. And okay, so let's see what we did. We know this and this now, right? We know this one, this one, this one, this one, and this one, and this one. So all we have left is this guy right here to try to find it. And actually, we could either use E or C. And so our strategy could be find it one, find it the other, just to check it. Maybe? Okay. So that's one reason why I wanted to leave plenty of room here. I wanted to do the check. I didn't leave enough room on my original thing. So if we go at E, right here, okay. So we're doing it E. So we're going to bring into the reaction force at E. That reaction is going to be here. This one we know, this one we know, this one we don't know. So that's the one we're trying to find out here. So we come in and go and I should declare my FBDs. I forgot to do that up here. Declare what it is that we're drawing right here, that it's a specific kind of thing. And maybe I can use some more space here. I don't need to crowd it too much. Here's our reaction. Here is, and here, going like that right there. So this is our FDE. This is our FBE. And this is an FCE, right? And DE is going to be in, DE is compression. BE is also in compression. So it would make sense here, taking a look at this is horizontal and this horizontal component. This guy must be also in compression. That's R. And I think by looking at these angles right here, that is our angle, and that's our angle, again, of 53.3. So if we take the, oh, and I should label this reaction is RE. I could have just put the number that's on there. That's 7,000 pounds upwards. So I think we could actually go in either direction here, either the sum of the forces in the x direction or sum of the forces in the y direction, and be able to find that, right? Because we know this and we know this, so we can find that. I think I decided to go in the x direction. Sum of the forces in the x direction equals 0. So what we would find is FDE is 3,000 pounds. FBE, and it's going to be FBE is 3,750 times the cosine of 53.13. And then we have, the only thing left is what we're trying to find, that's CE. And that's going to be times the cosine of 53.13. And we will find that FCE from this is going to be 8,750 pounds. And again, that's compression. So we've actually found all of them, but we want to maybe check at C, right? So coming back up at C, we'll see that we had a reaction that went upwards, right? Of R, well, take it back, went down. Remember that RC was down, right? Easy to make that mistake because it was drawn the other way up above. RC is down, and we're going to have a force coming out this way, and that's going to be FBC, and then we're going to have a force coming out this way right here, right? And that's going to be our FCE. That's the thing we just found, but this is another point that we could find it in, right? So we don't need it. Let me see. BC was something we found. Where do we find it? BC. Okay, right here, and it's 5,250, and it's in tension. So it comes in this way. So our conclusion is this must be in compression, that FCE. So we could take, actually we could take either way that we want to go. We could either go from the forces in the y direction or some of the forces in the x direction. Either way, because we know what this is in the y direction, so we're able to find out what this is because in the y direction. Or we could do it the other way. So there's a number of things where they cross over with each other. And I don't know if I actually found this out right here. So let's see, the sum of the forces in the, let's take the y direction. Y direction, and so we have a negative 7,000. That's what I found from way up here. A negative 7,000, and then so we're going to have FCE, and that's going to be times the sine of 53.13. And let me take that right here. So if I take 7,000, 53.13, take the sign, and then I divide it, and I get FCE equals 8,750 pounds. And we saw there was some compression. So therefore, it checks. And that is a method of joints for a long problem. Right? It's a pretty long problem, but you can do this. But it's the logic. It's a good overall, not just because of this is the topic that we want to care about. It's definitely something civil engineers care about, perhaps more than mechanicals do. It looks like I'm shitting here. But it definitely reinforces all the big concepts. So thank you for your patience here. And let's see, it's 25 minutes. That's a long problem.